Writing and solving model equations. Linear growth and exponential growth or decay can be used to model real-world situations. In this lesson, we will construct the two models, meaning linear and exponential, and compare their results. In future units and courses, even more models beyond linear growth and exponential growth will be discovered. Over time, we will begin to develop an appreciation for how mathematics can be used to model real-world phenomenon and how these models can be used to predict future events. Let's get started with some examples. Every year, the town of Algebraville conducts a survey to determine the population of their town. In 2010, their population was 4,670, and in 2015, their population was 5,480. This question or situation has three parts. Part A asks us to assume that the population of Algebraville has grown linearly since 2010 and that it will continue to grow in this way. What will be the population in 2021? Then in Part B, suppose instead that the population of Algebraville is growing exponentially. Write an expression for the population in terms of t, the number of years since 2010. And then in Part C, assume that the population of Algebraville has grown exponentially since 2010 and that it will continue to grow the same way. What will be the population in 2021? Round your answer to the nearest whole number. Let's begin solving Part A. Assume that the population of Algebraville has grown linearly since 2010 and that it will continue to grow this way. What will be the population in 2021? The key term in this question is linearly. That means we need to find the equation of a line. And the first step when finding the equation of a line is determining the slope, or in this application problem, its rate of change. And we're going to do that with the data points that are given to us in the problem. So 2010, the first year where the population was recorded in this problem, is going to be our x1 value. And the population that corresponds to it, 4,670, will be our y1 value. And then 2015, that'll be our x2 value. And its population of 5,480 will be our y2. So we're going to substitute these values into the slope formula in order to find the slope for this linear function. So we're going to have 5,480 minus 4,670 divided by 2015 minus 2010. If we do the subtraction, we're going to have 810 in the numerator and 5 in the denominator. And when we do the division, it'll end up simplifying to 162 people per year. We've just found that the slope, or rate of change in this application problem, is equal to 162 people per year. Now, the next step will be to find the y-intercept. There's another key piece of information in this first sentence. It's growing linearly since 2010. So in 2010, our time value, or our x value, we could either use x or t, is equal to 0. Therefore, our first initial point, 2010, 4,670, can be written as the ordered pair 0, 4,670. So therefore, our b value, or our y-intercept in this linear equation, is going to be 4,670. And now we can write our linear equation. We have our slope, we have our y-intercept. So the function will be the population in terms of time is equal to 162 times t plus 4,670. Now that we have the equation of our line, we can now determine what the population will be in 2021. Remember, in 2010, our t value is 0, so in 2021, our t value will be 11. So we can take P of t, which is equal to 162t plus 4,670, and substitute 11 in for t and evaluate. And when we multiply 162 times 11 and then add 4,670 to it, our final answer will be 6,452. Therefore, the population in 2021 is 6,452. Now let's look at part B of this question. Suppose instead that the population of Algebraville is growing exponentially. Write an expression for the population in terms of t, the number of years since 2010. Similar with our linear model, the years since 2010 tells us that this first point with 2010 and the population of 4,670 on our graph is going to be 0, 4,670. In an exponential model, this initial point, or the y-intercept, is also that a value when we're talking about y equals a times b to the x. We have our a value. It's 4,670. We also know in this problem that in 2015, the population was 5,480. If t, or time, is the years since 2010, the ordered pair for this point will end up being 5, 5,480. This 5 represents our x value, and the 5,480 represents a y value. So using this information and the exponential function y equals a times b to the x, we can then determine our missing b value by substituting these values in. We already know a is that 4,670. We have 5,480 as our y value, and then our x value is 5. So now we have to solve this equation. 5,480 equals 4,670 times b to the fifth. First thing we can do is we can divide both sides by 4,670, and when doing so, we'll end up getting that b to the fifth power is equal to 1 and 1,734 10,000ths. And now some of you may be asking, well, I've got this variable raised to the fifth power. How do I solve this? There are actually two ways to approach it. One way is to think about when you're solving, say, x squared is equal to some number. I'll just call it w. We take the square root of both sides, right? And because square root contains a plus or minus, you bring it over. This square root can also be written as an exponent to the 1/2. So we could write this as w to the 1/2 power here. And when you multiply exponents, they will, when you have a power to a power, you multiply exponents. So they would cancel one another out. We would be left with x to the first is equal to w to the 1/2. So we could end up raising both sides of this equation. Instead of to the 1/2 power, to get rid of the fifth power, we have to raise it to the 1/5 power. So if we put this into a calculator, 1.1734 raised to the 1/5 power, we end up getting 1 and 325 10,000ths as the answer for B. Now there's also another way to approach it. This is the algebraic way, using inverse operations. We could also instead graph our equation too. We had first b to the fifth. I'm going to write it as x to the fifth in the graphing calculator. And then it was equal to 1.1734. And I'm going to set it equal to y so that I get a horizontal line. And this we also have as y equals. And then if we find the point of intersection, this will also give us the correct answer for our problem. The answer here is 1.032, which is the same decimal, just rounded to the nearest thousandth place. And after we find our b, we can then write out our final exponential function. Y equals 4,670 times 1.0325 raised to the x power. The final step is to put our exponential function in terms of t, and we're using capital P of t for population in terms of time, being equal to 4,670 times 1.0325 in parentheses raised to the t power. Now let's look at part C. Assume that the population of Algebraville has grown exponentially since 2010 and that it will continue to grow the same way. What will be the population in 2021? Round your answer to the nearest whole number. Well, we already have our model equation, and the key words here are since 2010. That means in 2010, our time value is 0. Therefore, in 2021, our time value will end up being 11 because it's 11 years after 2010. So we can then take our exponential function model that we have, p of t, which is equal to 4,670 times 1.0325 raised to the t power, and substitute 11 in for t, and then we can evaluate it. So let's first rewrite our problem and put 11 in our t locations, and then we can get out a calculator and evaluate this. And when we evaluate it, we will end up getting 6,639 and a bunch after the decimal point, but it starts with a 0. That 0 rounds or keeps this 39 at 39. So the correct answer here is that the population will be 6,639 people. Now let's work through another example where we are writing and solving model linear and exponential equations. The Science Club is conducting an experiment to determine the decay rate for a certain type of cells. At the beginning of the experiment, there were 1,600 of the same type of cell. After the third hour, they measured 675 cells. Part A, based on the data from the beginning of the experiment and hour 3, Tanner claims that the number of cells C after hour H can be modeled by an exponential function. What is the number of cells predicted after 6 hours by an exponential model? And then part B, Gianni is also a member of the Science Club. She disagrees with Tanner and claims that the number of bacteria after each hour can be modeled by a linear function. Compare the function values for both the exponential model and the linear model at the second hour and the 5th hour. Let's begin with part A. Based on the data from the beginning of the experiment and hour 3, Tanner claims that the number of cells C after hour H can be modeled by an exponential function. What is the number of cells predicted after 6 hours by an exponential model? Okay, so he's saying that it's an exponential function. That means we are going to have y equals a times b to the x as our model equation. At the beginning of our experiment, that's when x or t is equal to 0. There were 1,600 of the same type of cell. So there were 1,600 or 1,600 cells. This is our A value. After the third hour, that's when x is equal to 3, they measured 765 cells. That's our y value. So we can then substitute these values into our equation. So we have 675 is equal to 1,600 times b to the third power. We can then divide both sides by 1,600, and when doing that, we will get 0.421875 is equal to b to the third. So in order to figure out b, we have to take the cube root of both sides. So you can either, if your calculator has a cube root button, you can use that and then type this entire decimal out. Or you could also write it as 0.421875 raised to the 1/3 power. And if we evaluate this in a calculator, we end up getting 3/4 or 75/100 as our answer. One could also graph these two functions because we had b cubed or x cubed if we're doing it in a graphing calculator, and we can set that equal to 0.421875, and we can see the point of intersection is right here, and the x value for that point is 75/100 or 3/4. So now we can write out our exponential function c, or the number of cells in terms of h, the number of hours, is equal to 1,600 times 75/100 raised to the h power, or 3/4 raised to the h power. Now we are not quite done with our question because it asks what is the number of cells predicted after 6 hours by an exponential model. So we have our exponential function, we found that. C of h is equal to 1,600 times 3/4 raised to the h power. Now that we have our function, we can figure out the number of cells after 6 hours by substituting 6 in for h. So we'll have 1,600 times 3/4 raised to the 6th power. And when we evaluate this in a calculator, we'll end up getting 284 and about 766 thousandths. Well, we should round this up to the nearest whole cell, so that's about 285 cells when we evaluate it fully. So this is our final answer, about 285 cells. Now let's look at part B. Gianni is also a member of the science club. She disagrees with Tanner and claims that the number of bacteria after each hour can be modeled by a linear function instead of an exponential one. Compare the function values for both the exponential model and the linear model at the 2nd hour and the 5th hour. Well, we already have the exponential model from part A, but now we have to determine the linear model that Gianni believes represents the function. So for a linear function, we need to figure out the slope, and we need to figure out our y-intercept, or b. At the beginning of the experiment, there are 1,600 of the same type of cell. Beginning of the experiment, that means that's our y-intercept. We can also write it as the ordered pair 0, 1,600. After the 3rd hour, they measured 675 cells. So after the 3rd hour, or an x value of 3, there are 675 cells. That's our 2nd ordered pair in this problem. So we have b already, it's the 1,600, but we need to figure out our slope. So in order to figure out the slope, we have these 2 ordered pairs, and we can substitute them into the slope formula. So we have 675 minus 1,600 over 3 minus 0. When we simplify the numerator, it'll be negative 925 over 3 in the denominator. And then when we do the division, it's going to go 308 1/3 times, or 308 and 3 repeating as the decimal, cells per hour. This means that the number of cells are decreasing at 308 1/3 cells every hour. We also know that the y-intercept is 1,600, so once we've found the slope, we can write our linear model to be y equals negative 308.3 repeating x plus 1,600, or you could write it as y equals negative 925 over 3x plus 1,600. And if you convert that as the number of cells being a function of h, it would be negative 308.3 repeating times h instead of x, plus 1600, or C of h is equal to negative 925 over 3 times h plus 1600. We're still not quite done with answering part B. We did find the linear function model, and we found the exponential function model in part A. So now we have to compare the function values for both the exponential model, and the linear model at the second hour and the fifth hour. So that's when t equals 2 and t equals 5. So if you'll recall, our exponential model is C of h, which is equal to 1,600 times 75/100 raised to the h power, and our linear model that we found was negative 925 over 3 times h plus 1,600. So let's first substitute t equals 2 into both. So we have 1,600, this will be C of 2, times 75/100 squared. You could also think of it as 3/4 squared. Well, 3/4 squared is going to be 9/16, times it by 1,600, or 1,600. Well, this is going to be 100, and this will be 1. 100 times 9 is 900. So C of 2 for our linear model is 900. And we should also label our answer as cells. Okay, now if we do linear, we'll have negative 925 over 3 times h, and we're evaluating it at 2, plus 1,600. Now, since this is not as nice of a calculation, we can substitute these values into a calculator, and when doing so, we'll get 983 and the decimal point of 3 repeating, or 983 1/3 cells, which is approximately equal to 983 cells if we round it. And therefore, after 2 hours, the number of cells calculated with our exponential model is less than the number of cells calculated with our linear model. Okay, so we compared the function values for both the exponential model and the linear model at the second hour. So now we have to do the fifth hour. So at the fifth hour, our time value in both of our functions will be 5. Let's begin with the exponential model. We're going to have C of 5 is equal to 1,600 times 3/4 raised to the 5th power. So we can bring out our calculator and evaluate this. And when doing so, we'll end up getting about 380 cells when we round it. And now let's do the same thing with our linear model. We're going to have negative 925 over 3 times 5 plus 1,600. So if we evaluate this, we end up getting 58 1/3, or about 58 cells. And therefore, after 5 hours, the number of cells calculated with our exponential model is greater than the number of cells calculated within our linear model.